students, so your midterm exams are ahead, and one of the most important and I'll say a bit confusing and difficult chapter that students feel is your D and F block elements, right? So to help you with this, I have brought a one-shot video on this chapter, and the entire video is very crisp and to the point questions because this chapter is completely theoretical. So you need to know all the reasoning questions. So I have brought you all the reasoning things here. Just revise this chapter from here and then your chapter will be done for your midterm. So let's get started quickly without getting delayed. So there are 8 topics in this chapter. The first one is transition elements and their position. Next we have electronic configuration. Then we have general properties of the elements. Next we have important compounds, inner transition elements, lanthanoids, actinoids, and then some applications of D and F block elements. Okay, so first of all, moving to the transition elements and their position in the periodic table. So what do we call, which elements are called as transition elements? Or first of all, we'll discuss about what is D block elements. Okay, the elements in which the last electron enters to the n-1 d orbital, those elements are called as D block elements. Okay, how many groups are there in the D block elements? There are 3 to 12, means total 10 groups are there from group number 3 to group number 12. Okay, now comes what is transition elements. So those elements which have partially filled d orbital in their oxidation state or in the atomic state or ground state, these elements are called as transition elements. Okay, now let's see the periodic table. So you can see here this one, group 3 to 12, this is D block. Okay, and in this D block, whichever elements are having completely partially filled d orbitals in their ground state and in their oxidation state, common oxidation state, are called as transition elements. Okay, now let's see about the electronic configuration of the transition elements. So the general electronic configuration is n-1 d, n2 10, ns1 to 2. Okay, and then in the transition in this D block there are 4 transition element series: 3D series, 4D series, 5D series, and 6D series. So if I show you in the periodic table, this first one which you see is 3D series, this one is 4D series, then I have this one is 5D series, and the last one is 6D series. Okay, 3rd series belongs to 4th period, 4D series belongs to 5th period, 5D series belongs to 6th period, and 6D series belongs to 7th period. Okay, so you can see here n-1 d, right? So the outer shell is n then. Okay, n shell will be the next number, so the period is decided in that way. Now we have electronic configuration. I want to show you for 3D series. It is 3D 1 to 10, 4s 1 to 2, the general electronic configuration. It starts from scandium to zinc. Next we have 4D series, 4D 1 to 10, 5s 1 to 2. It starts from yttrium to cadmium. Next we have 5D series, 5D 1 to 10 and 6s 1 to 2. It is from lanthanum to mercury. Next we have 6D series, 6D 1 to 10 and 7s 1 to 2. It is incomplete and actinum is the starting element, but the whole series is not completed yet. Okay, so you don't have to worry, you just have to focus on this 3D series and you should know the electronic configuration of all the elements in the 3D series. So if I show you the electronic configuration of all the elements in 3D series, you can see scandium is 3D1 4s2, then I have titanium 3D2 4s2, vanadium is 3D3 4s2, chromium should be 3D4 4s2. This is what was expected, but the actual electronic configuration is 3D5 4s1. Now what is the reason? Here one electrons comes from 4s to d orbital to get 3D5 configuration, and remember always 3D5 and 3D10. Okay, these are very stable configurations because 3D5 is half filled and 3D10 is fully filled. Okay, now coming to the next one, we have manganese again 3D5 4s2, iron 3D6 4s2, cobalt 3D7 4s2, nickel 3D8 4s2, copper should be 3D9 4s2. Okay, but again due to stability, what happens, one electron from 4s shifts to 3D and I get 3D10 4s1. Next we have zinc 3D10 4s2 configuration. Okay, now talking about some important points about the electronic configuration. So we can find exceptional electronic configuration from chromium and copper, that I have already shown you here, right? For chromium that is the exceptional, and the next one is copper here. 3D9 4s2 was expected, 3D10 4s1 is observed, 3D4 4s2 was expected, 3D5 4s1 is observed. Next we have zinc, cadmium and mercury of group 12 have fully filled D10 configuration. Okay, zinc, you have zinc, cadmium and mercury. So 3D, 4D and 5D, if I move, zinc, cadmium and mercury have fully filled in their ground state as well as in the common state. Hence they are not considered as transition elements. And what are they called as? They are called as pseudo transition elements. So the definition of transition elements is they should have partially filled d orbitals either in their ground state or in their oxidation, common oxidation state. Now if I show you the oxidation state of, so now if I just show you for zinc, zinc, mercury and cadmium, just a minute, yeah. So it's for zinc, cadmium and mercury. Okay, so the electronic configuration of zinc is 3D10 4s2, okay, 4D10 5s2 and 5D10, and we have 5D10 and 6s2. Okay, this is the electronic configuration for zinc, cadmium and mercury in the common oxidation in the ground state. So you see the d orbitals are fully filled, so we cannot call them as transition elements, because for transition elements the d orbitals should be partially filled. Now let's talk about their common oxidation state. Zn2 plus, cadmium 2 plus and mercury 2 plus. So in their common oxidation state, what happens? These two electrons are lost. Again we will have the configuration 3D10, 4D10 and 5D10. Right. So now if you see, since the orbitals, the d orbitals are fully filled in the ground state as well as in the oxidation state, common oxidation state, these elements cannot be called as transition elements. Then what do we call them? We call them as pseudo transition elements. Clear? Now there is example copper, silver and gold. Okay, copper, silver and gold. If I check the example now, see, copper, silver and gold. Copper electronic configuration is 3D10 4s1, silver is 4D10 5s1, okay, 5s1, and this is 5D10 and we have 6s1. Okay, now this is in the ground state. What happens in the common oxidation state? Copper has a +2 oxidation state, so I get 3D9. +2 means 1 electron will be lost and 1 electron will be lost from here. 2 electrons are lost, so 3D9. Then I have silver. Silver also can show +2 and +1, so in +2 also it has 4D9. Then gold shows +3 oxidation state, so it will have 5D8. Right. So now you see, in the common oxidation state, these elements have partially filled d orbitals in the common oxidation state. So since they may not have partially filled d orbitals in their ground state, but they have partially filled d orbitals in their common oxidation state, so that is why these elements can be considered as transition elements. Okay. Now moving forward, scandium is a transition but zinc is not. Again, scandium has partially filled d orbitals, zinc does not have, so that is why. Moving to the next topic, that is some physical properties. So we have 14 physical properties to discuss. The first physical properties is their metallic characteristics. Next we have enthalpy of ionization. Okay. Next we have atomic and ionic radii, ionization enthalpy, oxidation states, trend in M+2 to M reduction potential, M+3 to +2 reduction potential, higher oxidation states, magnetic fields, colored compounds, complex compounds, catalytic properties, interstitial compounds and alloy formation. These 14 properties we will be discussing in detail one by one. Very crisp and very important points. Majority of the questions will be from here. First, coming to the physical properties. Okay, so metallics, since they are transition metals, we call them, right? So they have the metallic properties. What are the metallic properties they have? High tensile strength, ductility, malleability, high thermal and electrical conductivity, metallic luxure. Then they are very hard metals. Okay, generally they are very hard metals. We have exceptions here: zinc, cadmium and mercury. Okay, next they have high melting and boiling point due to the metallic bonding. Again we have exception here: manganese and technetium. Okay, now let me tell you something about why they are very hard. So you have seen that these d block elements have incompletely filled d orbitals, or they have unpaired electrons in the d orbitals. So as a result of which, what happens, these metals can form a metallic bonding with each other, and this metallic bonding makes them very hard and their melting point increases. But here you can see exceptions is zinc, cadmium and mercury. So zinc, cadmium and mercury, as I have shown you just now, they have fully filled d orbitals, right? The d orbitals are completely filled. Now if their d orbitals are completely filled, we need unpaired electrons for metallic bonding, but these elements have completely filled d orbitals, so they do not participate in metallic bonding. So that is why these metals are very soft and they also have low melting point. Okay, now here there is an exception also for manganese and technetium. So if you see, manganese electronic configuration is what? Manganese electronic configuration is 3d5,4s2. Now you may ask, ma'am, manganese is having unpaired electrons, right? Then why is it not participating in metallic bonding, or why is it melting point is very low? So here is a very important thing, that manganese, although it is having unpaired electrons, but it is a stable d5 configuration. Stable configurations means it is very strongly attracted by the nucleus. Now when it is very strongly attracted by the nucleus, it cannot participate in the metallic bonding. So even though it has unpaired electrons, even though it is having the capacity to form metallic bonding, but it does not form metallic bonding due to its stability, and due to which the nucleus attracts it. So that is why it is having low melting point. Okay, you can see here the stable electronic configuration of manganese and technetium means that electrons are less delocalized, so they cannot move freely in the electron sea and cannot form strong metallic bonding. So here, even though there is unpaired electrons, there is no formation of strong metallic bonding because of stable electronic configuration. If it is clear, please put a comment yes, and let's move to the next one. What is that? Physical properties, that is what I showed you already. Yes, so melting point, let's see. This is a graph for the atomic number versus melting point. So you can see chromium, so melting point increases, right? As I move along the period, the melting point is increasing. Why? Because the number of unpaired electrons increases, metallic bonding increases, melting point increases. But manganese, what happens? It has a D5 configuration which is very stable, does not participate in metallic bonding. So that is why the melting point decreases here. Again, iron, cobalt, nickel. So if you see here, the melting point is slightly decreasing, and for copper it has decreased. So from iron, cobalt, nickel, the number of unpaired electrons also decreases. In iron there are 4 unpaired electrons, here I have 3 and here I have 2. Okay, iron, cobalt and nickel. And in copper there is no unpaired electron. So that is why it is having low melting point. Okay, and if you see in all the group, this molybdenum and tungsten, the group I can say the chromium one, okay, that chromium and molybdenum and tungsten have the highest melting point, because here chromium electronic configuration is 3d5,4s1, here it is 4d5,5s1, and here it is 5d5 and 6s1. So number of unpaired electrons is 6, which is maximum. That is why they have the maximum melting point. Now here certain exceptions, melting point increases up to D5 and then decreases. Now mercury, you can see mercury, like copper, mercury melting point is also very less because of no metallic bonding. So that is why it is found in the liquid state at room temperature. Then melting point of 3D series will be less than 4D and 5D. So you can see as we move from 3D to 4D to 5D, 4D and 5D will have more melting points than 3D. Now the reason for this is that when the metals are heavier, they have strong metallic bonding. Okay, so then you can see the highest melting point is for tungsten, and mercury is having the lowest melting point. These things you should remember. It can be asked in the form of MCQs. Now moving to the second thing, that is enthalpy of atomization. So what is enthalpy of atomization? The energy required to break an element into its atoms is called as enthalpy of atomization. Now here are certain things about enthalpy of atomization. So transition elements in general have very high enthalpy of atomization. Again, the reason is very same, because they have unpaired electrons, they have strong metallic bonding, so enthalpy of atomization is higher. So because of large number of unpaired electrons, there is strong metallic metallic bonding. Next again, because it is dependent on the number of unpaired electrons, and we know that in the middle of the series there are maximum number of unpaired electrons, so that is why the enthalpy of atomization is highest in the middle of the series. Zinc has the lowest enthalpy of atomization. Again, the reason here is because zinc has no unpaired electron, it cannot form metallic bonding. Next, enthalpy of atomization will be more for 4D and 5D than 3D. Again, the reason here is when the metals are heavier, the metallic bondings are very stronger. Okay. Next, we have the graph here. You can see as we move along the period, what happens? The number of unpaired electrons increases, so metallic bonding increases. Then comes manganese, which is having less metallic bonding because its electron does not participate in metallic bonding because of stable electronic configuration. Then again it starts to increase and then it decreases. Okay, so that is the trend you can observe in atomization. Now let's look at the next property, that is atomic radius and density. Okay, so atomic radius, if you see, it is a very unique property. We can see there is a very unique feature here. First, the atomic size decreases and then remains constant and then increases. Okay, so what is the reason for that? You can very easily see that along the period from scandium to manganese, the effective nuclear charge is very higher and that tends to decrease the size. Next, from iron, cobalt and nickel, the effective nuclear charge and the shielding effect is almost competing with each other. They are equal in magnitude, opposite in direction, I can say, so the size almost remains constant. Then from copper to zinc, the d electrons are completely filled now, right? So there is lot of inter-electronic repulsions, because of which the screening effect is more prominent and the size increases. Okay, and then talking about, if I down the group, if I go, so scandium to, so down the group the size should increase, right? So if you see scandium, yttrium and lanthanum, the size is increasing, but here you can see there is some changes, that is zirconium and hafnium, Nb, Ta, molybdenum, tungsten, Tc, Re, Ru, Os, these all size remains almost constant. Okay, now the reason for this we will know later on, but the reason for this is lanthanide contraction. So what happens exactly is, from lanthanum onwards, the next element, if you see, the next element, that is hafnium, there is 4f electrons are being filled, right? In hafnium there is 4f electrons, and these 4f electrons are what? They are poor shielders, means they do not shield the nuclear charge effectively. Why are they poor shielders? Because of their diffused shape. Okay, so now what happens, you can just imagine, suppose here there is the proton, then we have 4f, then we have 5d, and then we have 6s. Now this 4f and 5d are poor shielders, so what I will have, I can draw it like this. Okay, they are not very good shielders. So these orbitals are like this. So what happens, the nucleus charge or the nuclear charge reaches till the last of electron very tightly or strongly, and it pulls the electron towards itself, and that is why the size decreases. Okay, now moving to the next one, we have density. So density will increase along the period. Okay, coming to the next one, ionization enthalpy. So here there's a lot of things to understand. So ionization enthalpy in general across the period it increases, okay, but it has a lot of variations due to the stable electronic configuration. Now what are the variations, I'll tell you, but before that let me tell you some basic logic that you should know. So the first thing is, if we are moving from an unstable species to stable species. Now when I tell stable species, what are the stable species? D5, D10 and also D3. Okay, now why D3 is stable, that you will know in coordination chemistry chapter. For now just understand D5, D3 and D10 are the stable configurations. So if you are moving from unstable to stable, okay, that in that case the ionization energy will be required less. Okay, but if you are moving from stable to unstable, the configuration was stable and now you are making it unstable, it will be difficult to remove the electron, and in that case ionization energy will increase. Okay, I hope all of you please note down this one. This one concept can clear all your doubts. If you are moving from unstable to stable. Now when I say stable configuration, I have D5, D10 and D3 configuration. Okay, now these three configurations if I am reaching, then the ionization energy will decrease, and if you are moving from stable to unstable, ionization energy will increase. Now let's see the points here. So the first one, second ionization of chromium and copper are very high. Second ionization energies of chromium and copper are very high. Let's understand here. So what is the electronic configuration of chromium? Chromium is 3d5 and 4s1. And what is copper? 3d10 and 4s1. Right? Now see, second ionization energy. So if I remove second ionization energy, what I'll get here? Cr2 plus, right? So that means what? 3d4. 3d4, one electron will be removed from here, one electron will be removed here, 3d4 I will get. So this is an unstable species, right? If I have just Cr, first ionization energy, Cr plus, that is what? 3d5, this is a stable. Now from here to here you have to go, right? You cannot directly remove two electrons. First you will remove one electron, then you will remove the second electron. Now we are moving from a stable to unstable species. So that means in that case what will happen? The ionization energy will be very high. Similarly for copper. So what I will do for copper? For copper, from Cu to Cu plus I will get, it is 3d10, right? And then when you go to Cu2 plus, it is again 3d9. Right? So again you are moving from a stable to unstable state, right? So that is why the ionization energy will be higher here. Okay, so like this, on the basis of electron configuration you can explain all of them. So I'll just explain here, you need to understand this one. Now moving to the next one, this I have explained. First ionization energy of chromium is lower. First ionization energy of chromium. Chromium electronic configuration is 3d5 4s1. Now this is an unstable configuration, right? You have 3d5 and 4s1. Now if I have first ionization energy, I'll just give 3d5. So this was unstable and this was stable. So if unstable to stable I am moving, the ionization energy will decrease. So that is why this value is lower. Clear? Moving to the next one, I'll just write the law here. Means if I am moving from stable to unstable, then ionization energy will be higher. If you are moving unstable to stable, ionization energy will be lower. Stable, what it includes? D5, D3 and D10. Okay, please remember this rule, note down this, and based on that you can explain all of them, and I will show you how you can do that. So next we will move to this one, second ionization. So this I have explained, this I have explained. Second ionization energy of zinc is lower than copper. Let's talk about zinc. Zinc electronic configuration is 3d10 4s2. And what is copper electronic configuration? 3d9, sorry, just a minute, I'll write here so that I'll get a space here. So I have zinc configuration is 3d10 4s2 and copper will be 3d10 4s1. Now second ionization energy of zinc. Second ionization energy. So what is the first ionization energy? Zn plus, it will be 3d10 4s1 and second Zn2 plus will be 3d10. Right? Now for copper, if I move copper plus, it will be 3d10 and copper 2 plus, it will be 3d9. Okay, now you can see that here I am moving from a stable to unstable species. Okay, stable to unstable, here unstable to stable. So definitely this one will be easy, this one will be difficult. So ionization energy here will be lower and here it will be higher. So second ionization energy of zinc is lower than that of copper. I hope this is clear. If this you are getting, if you are understanding, please put me in the comment section that these concepts are clear. Very, very simple. Just you need to be a bit logical here to understand this. Otherwise, it's nothing difficult. We just have created a hype that this is very difficult chapter. Okay. Next, moving to the next one. Second ionization energy of manganese is less than that of iron. Let's see, manganese and iron now we are comparing. So now why I am explaining this, all these things is, any of this point can be asked as a 2-marker question. Explain why this trend is happening, why this is happening, explain. So you have to explain using the electronic configuration thing. Let's talk about this one. Second ionization energy of manganese. Manganese electronic configuration is 3d5 4s2, okay, and iron is 3d6 and 4s2. Second ionization energy. First ionization energy will be what? 3d5 4s1, and second ionization energy will be 3d5. You are removing one more electron, will get 3d. And we have copper for, sorry, second iron. So iron first ionization energy will be 3d6 4s1, and second one will be 3d6. Now see, here I am moving from a unstable to stable species, 3d5. Here there is no such stability. So definitely this value will be easy, this value will be lower than this one, okay. So that is the reason here. Next, we'll go to the next one. Third ionization of energy, third ionization enthalpy of manganese is more than that of Fe. Okay, I hope this is visible to you. You can see here third ionization. So this one I have already explained. Now I am moving to this one. Third ionization energy of manganese is more than Fe. Let's see manganese electronic configuration, right? So manganese is, let me come to this side. Yes, manganese and iron. Manganese electronic configuration is 3d5 4s2, and Fe is 3d6 4s2. Now manganese plus 1 is how much? We have 3d5 4s1. Fe plus 1 will be how much? I have 3d6 4s1. Next Mn2 plus will be how much? I'll have 3d4, okay. 2 plus, sorry, one more electron you will just remove, right? One more electron I am removing. So I'll get 3d5. And here Fe2 plus, just one more electron I will remove, that is 3d6. Next we have Mn plus 3, okay, you are removing one more electron here, 3d4, and Fe plus 3 we have, that is 3d5, right. So now what I can see here is Fe, you can see we are getting a stable configuration here. From Fe to Fe plus 3, if I move from Fe to Fe plus 3, I am getting a stable configuration. Whereas from Mn to Mn plus 3, I am getting a not a stable configuration. So that is why this value will be lower, this value will be higher, okay. Next, third ionization of copper, nickel and zinc is very high. Third ionization energy. So what is the electronic configuration of copper? 3d10 4s1, okay. Nickel we have 3d8 4s2, and zinc we have 3d10 and 4s2, okay. Now third ionization energy of copper, nickel and zinc is very high. Now here there is a very genuine reason that so let's discuss. So if I have first electron I have removed, second electron I have removed. Now when you are removing the d orbital electrons, the charge is also increasing here, right? First electron you have removed, it has become plus, then plus 2, then plus 3. So it is holding the electrons very tightly. So that is why when you have third ionization enthalpy, when you go such a higher value, the effective nuclear charge also increases. So removing the electrons becomes very difficult here. And here also I have an example. Yeah, this we have explained. This one is there, ionization energy of Mn plus and Cr plus. Mn plus and Cr plus. So if you see Mn, its Mn plus electronic configuration is 3d5 4s1, and Cr plus electronic configuration is 3d6 3d5, one second, yeah, so chromium is 3d5 4s0. Now when it is moving, first ionization energy, so you will remove one more electron from here, it will become Mn2 plus, so it will become 3d5, and here it will become Cr 3d4, okay, Cr plus Cr2 plus will be 3d4. Now we know that this is more stable, so this value will be less, this value will be higher, so that is why this is there, and this I have already explained here. So with this, from ionization energy, so many questions can be asked. You just need to know stable to unstable, then ionization energy increases, unstable to stable, ionization energy decreases. This is your mantra, Brahmastra for these questions, okay. Moving to the next one, oxidation states. So they have variable oxidation states, okay, because what is the reason for variable oxidation state? All the Ns, N-1d electrons participate. There is exception here, scandium and zinc have only one oxidation states. Next, Mn is the element which has the highest number of oxidation state, and also the highest oxidation state is also by manganese. Next, higher oxidation states are more stable down the group. So if you see chromium 6, then molybdenum 6 and tungsten 6, the higher oxidation states are of the heavier elements are more stable. Now let's talk about this thing, that is Fe3 plus is a more stable than Fe2 plus. Okay, so if you know why, Fe3 plus electronic configuration is what? 3d5, okay, and Fe2 plus configuration is 3d6. Now what will happen in that case? Fe2 plus will try to convert to Fe3 plus, means Fe2 plus is undergoing oxidation, so it will behave as a reducing agent. So you can see, if you just know this electronic configuration and what is stable and what is unstable, you can easily solve these questions. Next question, Cr3 plus is more stable than Cr2 plus. Now why? Cr3 plus is having D3 configuration and Cr2 plus is having D4 configuration, and I told you under stable configuration D3, D5 and D10. Now since this is more stable, that will move to this side, Cr2 plus will oxidize to Cr3 plus, as a result of which Cr2 plus is also a very good reducing agent. Next we have Mn plus 2 and Mn plus 3. Mn2 plus is D5 and Mn plus 3 is D4, right? So this is more stable. So if this is more stable, then this process will occur, Mn plus 2 to Mn plus 3 conversion will take place. It will undergo oxidation. Then that means Mn2 plus will behave as a, or Mn3 plus will behave as an oxidizing agent, or Mn2 plus will behave as an reducing agent. Okay, so Mn3 plus is undergoing what? Oxidation. Mn3 plus is undergoing reduction, and that is why it is behaving as an oxidizing agent. Now moving to the next property, that is oxidation states. So here are some important things. Higher if the oxidation state is there, then there will be more covalent character, and higher oxidation state, it will have more acidic character. You can see example out of Mn2O7 and MnO. Here there is more oxidation state, plus 14, 12, yeah, plus 6, here it is plus 2. So this, definitely this is more covalent character. And acidic character, if you see, this is plus 3, this is plus 2, plus 3, and this is plus 6. So higher the oxidation number, more will be the acidic nature. Next we have along the period, we will talk about some reduction potential. So along the period, what happens? The reduction potential increases. Okay, so as you know, the size is increasing, right? So the size is decreasing along the period, so the tendency to gain electrons becomes easier. Reduction is nothing but the tendency to gain electrons. So if the tendency to gain electrons increases, reduction potential increases, and that is why it becomes more and more it becomes lesser negative. It starts with a negative value and it becomes lesser negative, or I can say that the value increases. And here if the reduction plus 2 to m is easy, then the reduction potential value will be more. Okay, here you can see the trend, and you can see almost all the reduction potentials are negative, except there is one element, copper, which reduction potential is positive. Now we will see also why this happens, and you can also see the reduction potential depends on what factors. This is important question. It depends on atomization enthalpy, ionization enthalpy and hydration enthalpy. These three factors determine the electrode potential. Next we will see why copper is having this high positive value. So copper has high atomization and low hydration value. Okay, the ionization energy is not compensated by the hydration energy, and that is why the E0 value is positive. So you can see here that the second ionization enthalpy of copper is the highest value. Okay, and we cannot compensate it, so that is why the overall value comes out to be positive value. Moving to the next, plus 3 to plus 2 reduction potential. So here also first I want to tell you some basic rule. So if plus 3 to plus 2, okay, if you are moving from unstable, or just I'll tell like this, if we are moving from unstable to stable, okay, then reduction potential value will be higher, and if you are moving from stable to unstable, okay, then the reduction potential will be lower. Okay. Now under stable, here I'll add one more, D0, D5 and D10. These all are stable species. Okay, and D3 also, D0, D5, D10, D3. Okay, so now remember, here you should understand, unstable to stable, if you are moving, ionization energy decreases but reduction potential increases, and stable to unstable, if I am moving, ionization energy increases and reduction potential decreases. Okay, this please remember, please note down, very very important, helpful and the best trick to solve all these questions. So now I have hope you have noted down, I'll erase it. Now let's move for scandium plus 3 to scandium plus 2. Scandium plus 3 is having which configuration? Scandium is 3D 1 4s2, right? So if scandium 3 plus is there, this is D0 configuration. Scandium 2 plus will be 3D1 configuration, right? This is more stable, so I am moving from stable to unstable, so reduction potential will be low. So let me write down that here, stable to unstable, reduction potential is low, unstable to stable, reduction potential will be higher. Okay, so that is why here it is low value. Moving to the next one, Zn plus 3 to Zn plus 2. Zn plus 3 is D9 configuration, Zn plus 2 is D10 configuration. Again we are moving from unstable to stable, so reduction potential will have a higher value. Moving to the next example, Mn plus 3 to Mn plus 2. Mn plus 3 is D4 configuration, Mn plus 2 is D5 configuration. Unstable to stable we are moving, so high value. Next example is Fe plus 3 to Fe plus 2. Fe plus 3 is D5 and Fe plus 2 is D6, right? Again we are moving from stable to unstable. Again we are moving from stable to unstable. So that is why the reduction potential value will be a lower value. Okay. Next we will move to topic or the point 3.8, property stability of higher oxidation states. Here we have a lot of points to remember. Please understand, the metals, the transition metals in their higher oxidation states, okay, they form bond generally with fluorides and oxygen, means fluorines and oxygen. So we'll first talk about fluorine. Why fluorine? Because fluorine stabilizes the oxidation states, higher oxidation state. Here we have two examples. So if you see cobalt in its plus 3 state, vanadium in its plus 5 state, chromium in its plus 6 state, all these elements in their higher oxidation states are forming bond with fluorine. So with cobalt the reason is they have higher lattice energy, and with these two the reason is higher bond enthalpy. That means what? Now if the element in its lower oxidation state, if it form bonds with fluoride, they are highly unstable. Okay. But you can see then with elements when they are in lower oxidation state, they form bond with chlorine, bromine and iodine. Okay. Now you can find for copper in its, like here copper is in plus 1 state, it can form bond with chlorine and bromine and iodine. But here also we have something to important, if it is in plus 2 state, that is also lower oxidation state, in plus 2 state you cannot find I2, means it does not form bond with I, it only forms bond with chlorine and bromine. Now what is the reason for that? So Cu plus 2, as we see, its reduction potential is very higher, it reduces others and itself it gets reduces and it oxidizes others, so I minus present gets oxidized to I2. So that is why we cannot find CuI2. Next copper plus 1 and copper plus 2, if I tell copper plus 1, what is the configuration? D10 configuration, right? Very stable configuration, but these elements are unstable in the aqueous solution. So they are so unstable that they undergo a disproportionation reaction like this, where Cu plus is converted to Cu2 plus and Cu. Okay, this is a disproportionation reaction happening. Now the stability of Cu2 plus aqueous, this one, okay, rather than Cu plus aqueous is due to the much more negative hydration enthalpy of Cu2 plus than Cu plus. Okay, so here what happens, Cu2 plus is I can say has more hydration enthalpy than Cu plus, so that is why Cu plus is more stable than Cu2 plus. Moving to the topic, again stability of higher oxidation state. So I told you the higher oxidation state metals form bonds with fluorine as well as oxygen. So fluorine we have seen, now oxygen is also able to stabilize the higher oxidation states. Now the reason for this is, thus the highest Mn fluoride is MnF4, whereas for manganese it is oxygen. Okay, so if I see manganese has both higher oxidation. This is also higher oxidation state and this is also higher oxidation state. But +7 bond is formed with oxygen, whereas +4 is formed with fluorine. So that means oxygen can stable higher oxidation states better than fluorine. The reason for here again is the ability of the oxygen to form multiple bonds. Now moving to the next thing, that is magnetic property. So we have three types of magnetism: paramagnetism, diamagnetism and ferromagnetism. Paramagnetism means it is attracted in the presence of magnetic field. Diamagnetism means, okay, here there is a small error. Diamagnetism means strongly repelled in the magnetic field, and ferromagnetism means strongly attracted in the magnetic field. Now how do we calculate magnetic moment? There is a formula root over of n into n plus 2, where n is the number of unpaired electrons. Okay, number of unpaired electrons. Now moving to the next one, formation of colored compounds. So why these transition elements form color compounds? Because they have unpaired electrons which can undergo DD transition. Okay, so these unpaired electrons absorb color of one radiation, and the one they radiate complementary colors which lies in the visible region, and that is why they are so colorful compounds. You can see example, Cu2 plus absorbs red color and emits blue color, so the complementary of the red is blue. Okay. Next property we have, they form complex compounds. So the reason why they form complex compounds, this is important and you should remember these reasons why they form complex compounds: smaller size, higher ionic charges and availability of d orbitals. Next we have their catalytic property. So why they have catalytic property? So you should remember these 4 points. They have multiple oxidation states, large surface area, presence of incompletely filled d orbitals and the ability to form intermediate complexes. And we have certain examples here: vanadium in a contact process, Haber's process and catalytic hydrogenation. Now moving to the next one, that is interstitial compounds. So we have 4 points about interstitial compounds. What are interstitial compounds? First of all, when these transition elements are present, there are certain voids present in them, or there are certain empty spaces in which different atoms are occupying. Okay, so these spaces are called as I can say that is voids, or this type of compounds where these voids are filled with these type of atoms. They are called as that is non-stoichiometric, and they are called as interstitial compounds. And what are their properties? You can see here: high melting points, very hard, metallic conductivity, and they are inert substances. Now we'll go to alloy formation. So they can form a large number of alloys because their size is almost similar, their radius is similar, so that is why they form alloys. Okay, and there are some example here: brass and bronze, that you should see. Moving to oxides and oxoanions. So here I want to tell you first of all some important points, that all the transition metals form oxides except scandium. Okay, scandium does not form any oxide here. Next, this is important: as the oxidation number will increases, the ionic character will decrease, and hence the melting point will decrease. So ionic character decreases means the covalent character increases, and that is why the melting point will decrease. So CrO3 and V2O5 has low melting point. Now talking about amphoteric oxide, so V2O5 amphoteric, though mainly acidic, and it gives VO4 3- and VO2 plus salts. So which is the amphoteric example? You have to remember V2O5. So in vanadium there is a gradual change from the basic V2O3. So if I say V2O3, okay, to less basic V2O4, and then amphoteric V2O5. So if you see the oxidation, here it is +3, +4, and here it is +5. Right. So vanadium, this V2O5 is amphoteric in nature. So when this V2O5 amphoteric means it can react with both alkalis and acids. So it give you, when it reacts with alkalis, okay, when it reacts with alkalis, it gives you VO4 3-, and when it reacts with acids, it gives you VO4 plus. Okay, that you should remember. Next, another amphoteric oxide we have is Cr2O3. This is a must question. So 2 amphoteric oxides you should remember: V2O5 and Cr2O3. Okay. Next, we'll move to the next topic, that is important compounds. So here we have potassium dichromate and potassium permanganate. So basically we'll be studying about their preparation, structure and chemical reactions. So let us start with potassium dichromate. So this is a must question, methods of preparation, every year it is asked. So please remember this one. From iron chromate to sodium chromate, sodium dichromate to iron chromate to sodium chromate, sodium chromate to sodium dichromate to potassium dichromate. Okay, so this reactions you should remember. Balancing is important, so rewrite these reactions 5 to 10 times and just remember it. Next, what does it uses? It is used in leather industry and used as a very good oxidizing agent. Next, I'll talk about the structure. So CrO4 2-, this is a tetrahedral. Cr2O7, this is dichromate ion. This is also tetrahedral structure. Now here there's a thing you should remember, that these bonds are in resonance. These two are not in resonance, and these are also in resonance. Okay. Next, chemical properties. So CrO4 to Cr2O7 we can easily convert by adding or by giving them in acidic medium, and from Cr2O7 to CrO4 2- by giving them in basic medium. Okay. Next, we have here KMnO4 is an oxidizing agent, so it will oxidize many species. You can see some examples what it is oxidizing. I- to I2. Okay, I- to I2 it oxidizes. S2- to S, that also oxidizes. Sn2+ to Sn4+, Fe2+ to Fe3+. So these are all oxidizing by Cr2O7 2-. Next, we have potassium permanganate. So there are different methods of preparation of potassium permanganate. The most commonly used, you should be knowing about this commercial method and this method. Okay, so these two are commercial methods. So MnO2 is converted to MnO4 2-, then MnO4 2- is converted to MnO4-. Okay, this is the one where question is asked. So please remember this method properly with what is there on the arrow, that also you should remember. Next, the structure MnO4-. Okay, this is MnO4-, or we call it as so this is called as manganate, MnO4 2-, right? Yes, MnO4 2- manganate, and this is MnO4- permanganate. Okay, so here you should know both are tetrahedral structure. This is green in color, this is purple in color. Moving forward, we have the chemical properties. So chemical properties of MnO4-. So it is a strong oxidizing agent. Okay, it forms dark purple and it is isostructural with KClO4. This can be a MCQ question, so remember. Its intense color is due to charge transfer. It has a weak temperature dependent magnetism also. So next, thermal decomposition. When you have MnO4, it decomposes to K2MnO4, MnO2 and O2. So this reaction can be asked in fill in the blanks, like fill the reactions in that, or what happens when KMnO4 decomposes. So you should know this reaction. Moving forward, the oxidizing property. So here manganese, when it oxidizes others, itself it will get reduced. Now it has different properties of reduction based on the medium you are providing. So in acidic medium, Mn +7 here gets converted to +2, but in neutral medium it +7 gets converted to +4. Then we have +7 to, we have here that is +6. Okay, so you can see in acidic medium +7 to +2, neutral medium +7 to +4, basic medium +7 to +6. Clear? Now moving to next one, that is the chemical properties. We will see in acidic medium. So in acidic medium what happens? I- gets converted to I2. This example is important, I'll tell you why. Then NO2 convert to NO3, SO3 to SO4, right? You can see here NO2 is here in +3 state, right? And here it becomes +5 state. Oxidation takes place. Here it is in +4 state, here it becomes to +6 state. Here it is -1, here it is 0. Now we have next one here we have S -2 to S, Fe +2 to Fe +3, then you have if I see, this is +3 and here it is +4. So these are all oxidations taking place in the Which medium? Acidic medium. Now we'll talk about the neutral medium. Here important is this one. Again I told you, so in acidic medium I minus gets converted to I2, but in neutral medium I minus gets converted to IO3 minus. Okay. Next you have S2O3 to SO4 in the neutral medium, and Mn2 plus gets converted to Mn plus 4 in the neutral medium. Okay. Next we'll talk about inner transition metals. Okay, so first of all, in inner transition metals, what do you mean? The last electron enters to the n-2 f orbital or anti-penultimate subshell. Okay, the last electron should enter f orbital. There are two types of transition elements, inner transition. One is lanthanide series, another is actinoid series, 4f series and 5f series. So the general electronic configuration is noble gas n-2 f 1 to 14, n-1 d 0 to 1 or NS2. Okay. Now moving forward, here the lanthanides electronic configuration. So there are elements from cerium to lutetium. You can see cerium to lutetium 58 to 71, and the general electronic configuration is xenon 4f 1 to 14, 5d 0 to 1 and 6s2. Okay. And here if you can see, there are certain elements whose electronic configuration you should know. Cerium is there, then europium, gadolinium and ytterbium and lutetium. These elements electronic configuration you must remember. Next we have characteristics. So there can be a question, write 3 characteristics of lanthanoids or differentiate between lanthanoids and actinoids. So in those type of questions this can be used. So they are silvery white metals, hardness increases, good conductors. Then we have La3 plus and lutetium 3 plus, which are not colored, but in all other lanthanides are colored substance. Okay, then you have La3 plus and Ce4 plus. And we have Yb2 plus and lutetium 3 plus, which are except these ions all are paramagnetic. Similarly, next atomic sizes. So you know lanthanide contraction happens, so the electronic or the atomic size decreases, and this is because of the poor shielding effect of 4f orbitals. And here are certain consequences of lanthanide contraction. So first of all, the similar size of zirconium and hafnium, that's the first point. Covalent character increases, electronegativity increases, basicity decreases and standard reduction potential value increases. Okay, so these are certain points of consequences you should remember. This entire slide is very important. You need to know the reason of lanthanide contraction, what is lanthanide contraction and its consequences. Moving forward, here we have oxidation state. So general oxidation state of lanthanides is +3, +4 is shown by these elements, +2 is shown by these elements. Okay. Next color, so they are mostly colored due to the FF transition, and 4Fn and 4F14 minus n will have same color. 4F0 and 4F14 will be colorless because there is no unpaired electrons, right? Next we have magnetic properties. So lanthanum and lutetium, they are diamagnetic. Ce +4 and Yb2 plus, these are diamagnetic. All Ln +3 are paramagnetic, and Nd is the most paramagnetic material because it has most number of unpaired electrons. Then these are the reactions of lanthanoids. You can see you have it reacts with acid to give you H2 halogens LnX3, water LnOH whole 3 plus H2, LnC2 LnN with sulfur you will get Ln2S3, with oxygen you will get Ln2O3. Next here the uses is MiC metal. Next we will come to actinoids. So actinoids are the elements from thorium to lawrencium. Okay, Rn 5f 1 to 14, 6d 0 to 1 and 7s2 is the electronic configuration. You can see here, don't have to remember any electronic configuration. So the atomic sizes decreases due to the actinoid contraction, and that is due to the poor shielding of 5f orbitals. And next oxidation state, common oxidation state is +3, +7 is shown by Np and Pu, and +6 is shown by uranium. Moving to the next one, characteristics. So all actinoids are radioactive, silvery metals, highly reactive, paramagnetic in nature, slightly affected by the concentration of nitric acid owing to the formation of protective oxide layer, but highly affected by hydrochloric acid, and they form oxocations like NPO plus and EO2 2 plus. Okay, so these are the characteristics. Next, there are some applications of coordination chemistry, transition elements, some important application I'll tell you. TiCl4 with CH3 aluminium Ziegner catalyst is used to manufacture of polythene. Okay. Next, AgBr is used in photography. This you should know. Okay. Then PdCl2 is used as catalyst in oxidation in Volker's process. This one you should know. And then there is one more. One second. Yes, these 3 uses, please remember it, what metal is used, which process is there, you have to remember this one. Other uses you can just go and read. So that's all students in this chapter. The major part I have explained you very nicely, so please go through it, understand it, and in the next video we are going to solve questions. So all the best and thank you so much.